Welcome to the 21st lecture in our course on quantum mechanics. Last time, we took a look at quantum cryptography. We saw that by using the rules of quantum mechanics, Charles Bennett and Gilles Brassard solved a previously unsolvable problem, the problem of distributing a secret key for encrypting messages. Their scheme, called BB84, relied on the no-cloning theorem of quantum mechanics, the fact that quantum information cannot be perfectly copied. This time, we will talk a little about quantum information theory, the basic rules that govern information in the quantum world. Why would we do such a thing? Well, every age in history has a basic metaphor for the world, a way of organizing our thinking about the world around us. And in antiquity, a common metaphor was that the world is a huge organism with the different parts working together toward harmonious ends. Later on in the Enlightenment, after the work of Isaac Newton, the basic metaphor was that the world is a huge clockwork, a machine obeying perfect mathematical laws. And today, in the information age, we sort of inevitably think of the world as a huge network, a vast system of information exchange. The particles in the world do not just exert forces on each other and transfer energy from one to another, they send messages to each other. And what we want to do is we want to discover the fundamental rules of that information network. That's our business today. Now, all of this is based on something called information theory. There's a mathematical discipline called information theory, and it was developed around 1948, mostly by Claude Shannon of Bell Labs. And information theory was vital to the development of modern telecommunications, of computing, and so on. And in fact, Shannon's ideas have been among the most influential ideas of the 20th century. And the world is permeated by the concepts of information theory, the idea of bits, the idea of codes, the idea of information errors, and so on. Shannon's information theory is all about information resources and information tasks. And the basic question is, what resources are required to perform a given task? Now, the resources might include time, or storage space, or electrical power, and so on. Those are the resources we could bring to bear on performing a task. The tasks may include data storage, or overcoming noise, or maintaining privacy, and so on. So we're asking, what resources are necessary to perform what task? Now, Shannon's information theory, as important and powerful as it is, does not take quantum mechanics into account. It's a theory of classical information. The resources and the tasks it employs in the theory can be completely described in classical terms. And this works pretty well. Even today, we still use millions of electrons or millions of photons to represent each bit of data that we store or transmit. Nevertheless, Shannon's information theory has left something important out: the quantum nature of the world. Quantum information theory would include not only classical information, but also quantum information resources and quantum tasks. So in quantum information theory, we're going to identify three types of quantum resources. The first type is the bit. Bits, that's a resource. And what do I mean by bits? I mean that Alice can send to Bob, remember Alice and Bob are protagonists, Alice can send to Bob a 1-bit classical message, 1 bit of classical data. And if she can do that, she can use that ability as a resource. That's a classical resource. But then there are two quantum resources. The first one we've seen, qubits. We say that Alice can send 1 qubit of quantum data to Bob. If she's able to do that, she can use that in order to perform tasks that she may wish to do. The second one, though, is something that we haven't really talked about. The second one is E-bits. E-bits are bits of entanglement. In the E-bit resource is what you have if Alice and Bob share an entangled pair of qubits, say 2 spins in a total spin 0 state. This is 1 bit of entanglement. Now these different resources sort of have different characters. Bits are a classical resource. Qubits and E-bits are quantum resources. Bits and qubits are directed resources. Either Alice sends one to Bob or Bob sends one to Alice. And that matters. It's different. If Alice sends a 1-bit message to Bob, it's a different resource than if Bob sends a 1-bit message to Alice. E-bits, on the other hand, are undirected. They're merely shared. It doesn't matter how Alice and Bob came to share the parts of an entangled pair of qubits. They just share them. That's the resource that they can bring to bear on solving information tasks. Now, nobody has done more to sort out this question, the question of what resources are important and what you can do with various resources, than Charles Bennett. Charles Bennett is an IBM physicist. As you recall, he helped to invent quantum cryptography, and also, as we will see today, he's helped to invent many other fascinating ideas in quantum information. And Bennett has tried to summarize some of the basic principles about quantum information into a set of rules. And in fact, he is the origin of the term E-bit. So when E-bits appear in the rules, he was part of the invention. And we're going to call these rules that Bennett has tried to put together Bennett's laws. And every one of Bennett's laws looks like this. You have X, and you have a funny little symbol, and you have Y. So what's the funny little symbol? The symbol between X and Y means can do the job of. And that means that the resource labeled X is able to perform the same task as the resource labeled Y. It may be able to perform others as well, but X can do the same job as Y. So let me give you a homey example so you know how to do this. Suppose I have 2 different kinds of resources. I have dollars and I have bottles of drinking water. Now it turns out there's a grocery store nearby, and at the grocery store, bottles of water cost $1. So that means if I have $1, I can go to the grocery store, buy a bottle of water, and drink it. It's just as good to have a bottle of water or to have a dollar. When I can buy a bottle of water, I can get a drink either way. So $1 can do the job of 1 bottle of water. We can use $1 to buy a bottle of water. However, the store is not buying back bottles of water. And that means that if I have a bottle of water, I cannot use it to obtain $1. And so it isn't true that 1 bottle of water can do the job of $1. The dollar is a stronger resource, a more powerful resource than a bottle of water in our example. Okay, so let's go through Bennett's 4 laws of quantum information. The first law is actually something that we've already seen. Bennett's first law says that 1 qubit can do the job of 1 bit. What does that mean? It means that we can send 1 qubit from Alice to Bob and use this qubit to send a 1-bit classical message. And we already saw this. Alice can use the qubit to send 1-bit message. She can encode her message in the Z component of a spin state, for example. 0 is spin up, 1 is spin down. And then when the qubit reaches Bob, he can measure the Z component of the spin and figure out what the 1-bit message is. It's not true that 1 qubit can do the job of 2 bits. We found that we could not put 2 bits of classical information into a 1 qubit quantum message. So 1 qubit's not more powerful than 2 bits. Alice can't send 2 bits to Bob in 1 qubit. Right. All right. So 1 qubit can do the job of 1 bit whenever we want. The second of Bennett's laws, Bennett's second law, is just as easy to understand. It tells us that 1 qubit can do the job of 1 e-bit. In this, we can imagine that Alice makes a pair of spins in her own laboratory in a total spin zero state. She can do this. Nothing can prevent her from doing this. And now Alice uses her ability to send a qubit to send one of the spins to Bob. And afterward, Alice and Bob share an e-bit. So if Alice is able to send qubits to Bob, then they can use that to come to share e-bits. They can use qubits to buy e-bits. Oh, they could also do it the other way, of course. If Bob can send a qubit to Alice, he could make a pair of entangled spins in his laboratory, send one of them to Alice, and then they would share an e-bit. A qubit either direction is enough. A qubit in either direction can do the job of an e-bit. What this means is that qubits are the most capable of our 3 kinds of resource. We can turn a qubit into a bit by using it to send a classical piece of information. We can turn a qubit into an e-bit by using it to distribute some entanglement that we made locally. Qubits are the strongest. All right, what other connections might we have? For example, can we send messages? Can we send bits using e-bits? Can we send 1 bit using 1 e-bit? Can we send classical information using only entanglement? And the answer is no. Entanglement by itself cannot be used to send either classical or quantum messages. Entanglement by itself doesn't let you do anything like that. Now, back a few lectures ago, when we were talking about the no cloning theorem, we did tell a science fiction story about using e-bits to send messages faster than light. But in order to do that, we needed to use a magic quantum cloning machine, and that was what enabled us to use an e-bit to send a bit. Such machines don't exist. An e-bit does not allow us to send a bit. However, even though entanglement by itself will not allow us to send messages, it will turn out that entanglement can actually assist us in sending messages. And that's the subject of Bennett's third law. This one looks a little more interesting. It says that 1 e-bit plus 1 qubit can do the job of 2 bits. This is a weird one. And it was discovered by Bennett and Stephen Wiesner in 1992. And this is sometimes called dense coding. It's not a very good term, dense coding, but it's called that because somehow, even though 1 qubit is used, 2 bits get sent. It's like there's twice as much information as you might expect. And here's how it works. We imagine that Alice and Bob initially share 1 e-bit, say 2 spins in the total spin zero state. And then Alice takes her qubit and she rotates it, perhaps using a magnetic field. And she chooses one of 4 possible rotations. I'll just tell you what those rotations are, actually. She can do no rotation at all, that counts. Or she can make a 180-degree rotation around the x-axis, or around the y-axis, or around the z-axis. That's 4 possible rotations. And because there are 4 possible rotations, she could use her choice of rotation to represent 2 classical bits of information. The 2-bit messages 00, 01, 10, or 11. So, Alice and Bob started out with a total spin zero state. Alice rotated her qubit one of 4 different ways, and now she sends her rotated spin, her 1 qubit, to Bob. 1 qubit from Alice to Bob. Now Bob has both qubits. Well, it turns out that Bob can make a measurement on his pair of spins, a joint measurement on the pair of spins. And this measurement is called the Bell measurement. And I'll skip the details. The point about the Bell measurement is it measures the type of entanglement of the spins. And because one of the spins may have been rotated, the type of entanglement has changed. And in fact, by making the Bell measurement, Bob can actually tell exactly which rotation Alice made. Therefore, he knows exactly which 2 bits of information she wanted to send. he can read Alice's 2-bit message. Now, this is weird and unexpected, because by itself, 1 E-bit cannot send any information. 1 E-bit is worth no bits. And by itself, 1 qubit can send only 1 bit of information. But together, they can send 2 bits of information. Now, there are 2 qubits involved, but Bob has been holding on to 1 the whole time. So let's take a look at this process by making a kind of Feynman diagram of the process. In the diagram, time goes up. We read the diagram from bottom to top. And so at the very beginning, our E-bit is created somehow and shared so that Alice on the left-hand side and Bob on the right-hand side each have 1 part of the E-bit. And then Alice makes her rotation on her E-bit. And this rotation is determined by the 2 bits of her input message. And then Alice sends her qubit over to Bob. Bob now possesses both qubits. He makes the Bell measurement. He reads the output. The Bell measurement gives 2 bits of output and tells him exactly what Alice's message is. Now, I remember the first time I saw this picture. Charles Bennett was showing me this at a conference we were both at, drawing the picture on a piece of paper in his hotel room. And I remember my feeling of absolute astonishment at this, because I knew that a qubit can only carry 1 bit. I knew that mathematically, I could prove it. But here, somehow, even though Alice only sent 1 qubit to Bob, she could send 2 bits of information to him. But of course, there are 2 qubits involved. So I looked at the diagram and I made a joke. I said, oh, well, of course, 1 bit of information goes across with the qubit, and the other bit of information goes back in time to the formation of the E-bit, and then forward in time on Bob's side. So half of the information goes back in time and gets to Bob that way. Well, does information really go back in time here? Maybe not quite. But even if that's not the way to describe it, even if that's not the right language to use, there's certainly something very peculiar going on in Bennett's third law. Amazingly, dense coding was not the biggest surprise in store. The biggest surprise, I think, was quantum teleportation. Quantum teleportation is the subject of Bennett's fourth law. Here's the teleportation law. 1 E-bit plus 2 bits can do the job of 1 qubit. So the idea is that Alice and Bob initially share 1 E-bit, 1 bit of entanglement. And Alice also has a qubit that's in some quantum state that she doesn't know, but she'd like to transfer that qubit to Bob. Now, if she could just send the qubit to Bob, that would be easy. But for some reason, we're not going to do it that way. What Alice does is she takes her half of the E-bit and her input qubit, and she makes a Bell measurement on her 2 qubits. Now, at first, that seems completely destructive. First of all, this measurement completely wipes out her original. That unknown state that she had is completely destroyed. Furthermore, the result of her measurement tells her nothing about what that state was. It looks like she's just done something destructive. But she got 2 bits of classical information out of the process. So she transmits that any way she pleases. US mail would be fine. She transmits that to Bob. So what does Bob do? Bob gets 2 bits of information from Alice. So he uses that 2-bit message as instructions for how to rotate his qubit. And once again, he does exactly the same rotations that were used in dense coding. He either does no rotation at all, or he rotates by 180 degrees about the x-axis, the y-axis, or the z-axis. And which rotation he chooses is based on the 2 bits of information, one of 4 possible messages, that he gets from Alice. What's the result? Afterward, almost magically, Bob's own qubit, which used to be half of an e-bit, is in the original state, the original quantum state that was destroyed by Alice's measurement. Somehow that state has just appeared over at Bob's side. And how did that get there is your reaction to this amazing fact. And the how did that get there question is exactly why they called it quantum teleportation. The quantum teleportation process was actually discovered in 1993 by 6 physicists meeting at a workshop in Montreal. And this is a great example of the power of collaboration and discussion to sort of break new ground and find out new surprising things. The list of people who are responsible for quantum teleportation includes many people that we've met before in these lectures and many that we'll meet again. It included Charles Bennett from IBM, no surprise. It included Gilles Broussard, the other half of BB-84 from the University of Montreal. It included Claude Crépeau from McGill University, a cryptographer. It included Richard Josa, who's now at the University of Bristol, who was a pioneer in quantum computing, and we'll meet his work in the next lecture. It included Asher Paris. We've been quoting Asher Paris saying, "Unperformed experiments have no results," a deep thinker about quantum theory. And it included William Wooters of the no cloning theorem. So the group of people that invented quantum teleportation is a wonderful nucleus of some of the great thinkers about quantum mechanics and information. Now, before I leave off talking about quantum teleportation, I should clear up some misconceptions. The first one is that teleportation is about information transfer, not transportation. The teleportation process sends 1 qubit of quantum information from Alice to Bob. And in the laboratory, it is barely possible to do quantum teleportation to send 1 qubit from one side of the table to the other in an optics lab, for example. Now, teleporting the quantum information in a human being would be, I estimate, 10 to the 27th times harder. That's a 1 followed by 27 zeros. That's 1,000 trillion times harder than teleporting 1 qubit. And we need lots of e-bits to do it. Huge amounts of entangled matter. Well, we can make e-bits, but making them in those numbers is a bit daunting. And so it's not about transportation in any sense. Teleportation is also limited by the speed of light. Until Bob gets his 2 bits from Alice, he does not know how to adjust his qubit so that it will be in the original state. Until the 2 bits arrive, his state is essentially random. Now, also, because of the no cloning theorem, we should remember that the original qubit, Alice's input qubit, must be wiped out. This is not like an ordinary communication channel for classical information, because in classical information, the fact that I send you a message doesn't necessarily mean that I have to destroy the message on my end. But because of the quantum no cloning theorem, if Alice sends a qubit to Bob, she must destroy her qubit in the process. She must no longer have it. Finally, I want to just point out one more thing about teleportation. What Alice actually sends to Bob are just bits of information. Can you send a qubit using bits? Now, we previously said that that it would take many bits to send a qubit, if we could do it at all, which is doubtful, because it would take many bits to describe the amplitude numbers in the superposition state of a qubit. And so it would just take many, many, many bits. In teleportation, therefore, since you only send 2 classical bits, most of the work must be done by the E bit. So once again, if you look at the diagram we drew for the teleportation process, most of the quantum information must actually somehow flow along the E bit. It must go back in time, so to speak, to the formation of the E bit and forward to Bob's end. And we just need the 2 bits of classical information to finish the job. A very strange way of looking at it. Okay, what's quantum teleportation good for? Why would you want to do quantum teleportation? Why would you want to send quantum information in this way? Well, just for the sake of argument, suppose Alice can send qubits to Bob only occasionally, only on Thursdays, say, and other days of the week there are too many cosmic rays or something like that. She can only send qubits to Bob on Thursdays. She can send classical bits anytime. They're easy. So what Alice and Bob do is that on Thursday, Alice and Bob use their ability to send qubits to make a lot of E-bits. Now they can do teleportation anytime they wish. They can store up, in other words, the quantum communication part for use later. And this is not at all like classical communication. We can't use signals that we transmitted yesterday to send today's news. But you can almost do that in quantum mechanics. Also, they could make the E-bits by sending qubits not from Alice to Bob, but from Bob to Alice. And this is a little weird. So sending a quantum message from Bob to Alice, 1 qubit allows you to make an E-bit by Bennett's second law. And sending a classical message from Alice to Bob, 2 bits, together let us send a quantum message from Alice to Bob. Lets us do quantum teleportation. This is also not classical. We can't use a signal I sent to you yesterday to get today's news from you to me. Something very strange is going on in quantum information theory. So here are Bennett's 4 laws. The first law, a qubit can do the job of a bit. We can send classical messages using quantum signals. Bennett's second law, a qubit can do the job of an E-bit. We can use quantum signals to set up entanglement between Alice and Bob. Bennett's third law, dense coding. An E-bit together with a qubit can do the job of a 2-bit classical message. And Bennett's fourth law, quantum teleportation, an E-bit plus 2 classical bits can do the job of a qubit. Once you have Bennett's laws, you can play lots of interesting games with them. For example, if classical bits cost nothing, and as a practical matter they are a lot cheaper than qubits these days, if classical bits cost nothing, then qubits and E-bits are worth just the same, because I can always use a qubit to make an E-bit, and with some classical information that's free, I can use an E-bit to send a qubit in quantum teleportation. So if classical information is free, qubits and E-bits are worth exactly the same. And also, sending a qubit from A to B is just the same as sending a qubit from B to A, because either way, I can set up E-bits and then use it for teleportation, because classical signaling is free. Well, here's a stranger game you can play. Suppose E-bits cost nothing. It's a very strange idea. E-bits are not cheap, and we really don't know how to keep them around very long. But suppose we could. If E-bits are free, then 1 qubit is worth exactly 2 bits. If you have one, you can make the other. Okay, what have we found out? Some of the rules for the quantum information network have been sort of outlined in the course of our lecture. And these rules, Bennett's 4 laws, are sort of clues to how nature itself moves information around. And there's something funny going on with entanglement. We can't use entanglement all by itself to send messages at all. But if we have some entanglement, we can do some surprising stuff. We can send messages more easily, or the entanglement can help us send messages that we wouldn't otherwise be able to send. And when we try to analyze how that works, we're tempted to say that some signals actually go backward in time. Now, there are no time travel paradoxes involved here. This backwards in time signaling only happens, if you will, where you can't see it, as usual in quantum mechanics. It only happens if you don't actually find out what the message is. And anyway, this idea of sending information backwards in time might not be the right language for talking about what's going on. But whatever's going on, it does make a difference in dense coding and teleportation, Bennett's third and fourth laws. So, what's next? Next, we're going to investigate other opportunities. We're going to investigate quantum computing. In quantum computing, we're going to harness the power of quantum mechanics to solve math problems. It turns out that just as qubits can exist in superpositions of basis states, they can be not just 0 or 1, but also weird combinations of 0 and 1, so quantum computers can have superpositions of different memories. And they can run superpositions of different programs. Could such devices really exist? And if they did exist, what would they mean? That's next time. I'll see you then.